So two big pieces of evidence for the Big Bang Theory are this. First is the detection of the very initial time, the hiss of the birth of our universe. And I'll try to kind of convince you of that. And the other is, in general, when we look at our universe, the beginnings of our universe, remember when we look at distant stars or distant regions of our universe, we are looking back in time. We can see that the abundance of the early atoms, hydrogen and helium and lithium, that matches up with the Big Bang Theory. I love saying Big Bang Theory. Okay, so starting with kind of the background radiation, actually in the microwave region of the electromagnetic spectrum, as being kind of the hiss of the birth of our universe. So these guys, actually back in the 1960s, were operating, this is a radio telescope back there, and they were picking up some kind of pesky sort of radio waves in the microwave region of the electromagnetic spectrum, and it was kind of static. It was static, and they wanted to eliminate it, or they couldn't eliminate it, and so they traced it down to actually what they were listening to or picking up was, like I said, the overall kind of remnants, the hiss of the birth of our universe. Amazing. So I mentioned that they picked up this hiss in the region of the electromagnetic spectrum we call microwaves. And just to kind of remind you, we talked about the electromagnetic spectrum. And remember that we have these shorter wavelengths than visible light. We have visible, and then shorter wavelengths will be ultraviolet, shorter than that X-rays, and then we have gamma rays. And then we have these longer wavelength radiations. So longer than visible, we have on the other side of red, we have infrared, and then we have radio waves. And within radio waves, we have a region called microwaves. So I just kind of wanted to remind you of that, how that works. So if we go back to kind of the segue between the era of nuclei and the era of atoms, remember we said that time of 380,000 years after the Big Bang is an important time. And so actually I mentioned that before the electrons kind of settle down and associated with themselves with nuclei, there was more chaos in the universe, and it would not allow the streaming of this information now that we pick up ever since the era of atoms occurred. So you kind of see here is the chaos before, where we have free moving electrons, and here is kind of the settled down universe where actually now we can get the information. And so actually what they were picking up in microwaves finally, or actually, was this information. Let's see if this hot link works. Yeah. So let me show you. I'm going to play this little animation, and you kind of look at, if you want to, the temperature kind of cool down here. Remember, we'll just look at the temperature cool down and look at what's happening. We're going from the era of nuclei to the era of atoms. Okay, notice that those electrons are not associated with nuclei yet. The universe is cooling down, electrons associated with nuclei, and now we have that those photons of energy can escape. It's not as foggy. I've heard it kind of described. So at this time, at this particular juncture, the temperature was about 3,000 Kelvin. And so that makes, remember we said that actually temperature will translate to a certain wavelength of energy, and that corresponds to peaking in the visible or infrared region of the electromagnetic spectrum. Well, if we go ahead and take that temperature, 3000 Kelvin, and apply the fact that we know our universe has been expanding ever since the Big Bang, okay, we definitely have a fair bit of redshift going on, and that redshift we know would go ahead and take that temperature and shift it down 1,000 times. And that now wavelength we should be looking for at that particular temperature that long ago would be about this 2.73 Kelvin. And that corresponds to a temperature in the microwave region of the electromagnetic spectrum. And that's all due to the redshift. Okay, so pretty cool. I'm going to go ahead and play this for you too. I'll play it and then see how much explanation it needs. Looking down, finding the Earth or our star system in the disk of the Milky Way galaxy. There's the fabric of space-time. So we can map from our perspective, you know, a fair bit of this visible information would be the Milky Way galaxy. Visible, infrared, near infrared, far infrared, longer wavelength. Increase the contrast. Okay. So we have arrived at, I don't know if you see this, but this kind of stuff here in this in the microwave region of the electromagnetic spectrum, that miscellaneous information actually is the hiss from the birth of our universe. It's kind of the static from the birth of our universe. So this map that you're looking at actually was taken by a gizmo called the W map. And let me go ahead and show you that gizmo. But what this is a map of our universe from our perspective, looking at that background radiation. And it's abbreviated Cosmic Microwave Background, CMB radiation. And again, it's associated with the birth of our universe. So NASA has great websites. Now, this W map actually was put in orbit or launched in 2001. And just would encourage you to visit this NASA website at the W map. And again, I have birth of our universe down here. So the other big thing that supports our current, the Big Bang theory, as we've been talking about, is just generally speaking, the abundance or how much there is of the elements, the simplest elements. The simplest element is hydrogen, followed by helium, and a little bit of lithium actually was present back in the early part of the universe, early times of the universe. So let's see if this does it for you. Actually, all things considered, we would expect kind of the ratio, according to the theory we've been talking about, to have about 3 times as much hydrogen as there is helium. And that is indeed the case. Another thing is that the expected amount of let's see how to explain this. The expected amount of hydrogen, which actually heavy hydrogen, deuterium, and the expected amount of helium, it's going to be the blue line, and the expected amount of lithium, it's going to be the purple line. If we were to have 4% normal matter in our universe, actually falls pretty darn well. So the red or the kind of brownish line is deuterium or hydrogen, and the blue line is helium, and the third heaviest atom then, and there was a little bit of lithium present in the early universe, is the purple here. And so what you're looking at is the comparison of the actual, which are the kind of the solid horizontal bars, to the predicted at assortment of normal matter present in our universe. So bottom line is the abundance of those three elements also fit quite nicely with the Big Bang Theory. At 4.4%,